this morning, we learned that the Oak Ridge National Supercomputing Center, it became #1 again. Previously, it was Chinese system, and we were #3 for the last year or so in Europe. Europe in general is investing in supercomputing, but not following this race, which in some cases they call it a beauty context. So let's just step aside from this big iron race and focus on the problems we solve here. And precisely for that reason, I chose the title Grand Challenges and the Role of Supercomputing. It's not about computing for the sake of computing. There are real socio-economic problems that these computers are used to solve. So I have been CTO of CSCS. What that really means? It means that my role involves architecting system, making sure they work as a whole because they have many, many moving, thousands and thousands of moving parts, and applications run on it. And I started working in this area right about when I started my PhD, roughly just under 20 years ago. And it's just such a fascinating field. And I'll tell you why it's so fascinating over the course of my talk, that still today, I'm really excited to work in it. And I hope for those of you who are starting their career or early part of your career, oh, something disappeared. Because I didn't move it. Oh. I can assure you I have more than one slide. Oh, okay, it's my, yeah, it's not connected to the big system. This is a little bit, okay, so I'll make sure this. And by the way, the slides are on Google Cloud thing, so this should. So this is my first slide, and I cannot really, in no way, most of the work I will present here, I can acknowledge people, because majority of the work I will present about this grand challenge of climate and weather modeling, it's done in collaboration with people at CSCS, which is the Swiss National Supercomputing Center, Matthew Swiss as an application partner, and our vendor partners, which involve NVIDIA and Cray. But supercomputing has always been about multidisciplinary efforts. So there is not one expert that knows everything. A large group of people from domain science, mathematics, algorithms, system designer, programming language, they come together to solve a single problem, and that makes it so exciting. Because you learn and advance not only your field, but you help in learning and advancing other fields of science. So that's really rewarding, in my opinion. So when you now think of supercomputing and big computers, always think of large inter and multidisciplinary teams. So what you see from the one picture, I took it from my cell phone, looking at the weather of Porto. It was a little bit misleading, I would say, but never mind. They're probably using nowcasting, which is accurate for a short time span. But what we see now these days, at our personal lives, we just take it for granted. When we go, we travel, whether we should take umbrella or a jacket or not. We can plan up to 7 or 10 weeks in advance. And there are, and so you see a picture of a cell phone with the app. So there is not just one application, there are many other. And I'm pretty sure for one reason or the other, you will have your own. So the one other one is the Matthew Swiss application, where you can see Swiss weather with, I hope it's not creating. So this is, on a personal level, weather forecasting affects us. But there are other parts where it becomes almost matter of life and death. I think I should move it a little bit. So what you see here is a picture of what in Switzerland they call it flood of the century. So I copied the caption here. And it was just a very small village or valley in Switzerland, where there are a lot of them here. And these floods created a human, I mean, Switzerland is a rich country, so it created a massive human disaster for businesses and for people. And now they don't want to forget it, so they still take people to show them around. But what they learned there is, with the weather forecasting and some of these early signs, why did they miss the intensity of this event? Because it was not that long ago. It was not a century ago, only just over 10 years ago. And then they realized is weather prediction is a prediction. You are making, it's a probabilistic attempt to predict what happens next. So if you make only one prediction or a handful of prediction, you may choose some initial conditions in your simulation where you can miss extremes. And then they realized if they have done more predictions all in parallel in weather modeling, they call them ensembles, they would have detected the intensity of this event. So what they realized is not only we have to model and predict what is happening in one scenario, but we have to do it in multiple scenarios. So that was another. The other thing where you say, okay, weather and climate is normal, why should we suddenly start worrying more about it than less? The other thing is we all travel. I came and took a plane to come here. Air travel is growing by leaps and bounds. It's the number, I mean, there are some statistics here from the Dubai airport and some statistics that was given in 2017 that all across in every region, both passenger and freight cargo travel have broken all record. In some place in India, and it was not a big airport, they said they flew almost 1,000 flights. And if you just think about it, and all of you may have canceled, delayed, and all these events with your flights, and what's happening is, okay, in some cases there could be a technical issue, but in majority of cases it's weather related. Like yesterday, my flight coming in and out was delayed because of some weather conditions over the way. And you just have to imagine that all these planes in flight, not only they have to know what is happening, but what is happening at different altitudes at different levels. So you have to not only get, okay, if it's going to be sunny or rainy, but you have to determine a lot of conditions at different, so planes can land safely and get out safely. Another thing which has a huge impact to almost the entire world population is the effect of climate, or in this case, I'm moving more from a short-term effect to a long-term, is on agriculture, crop. There are some estimates that if certain regions, all of them get drought at the same time, millions of people can even die. And that is something that we have to be able to predict, so we can take some preventive measures to maybe store food. So in this picture, what you see is there cannot be just one impact. There could be impact on biodiversity of the environment, agriculture, farming, and these patterns sometimes can have an effect starting with a small impact and leading up to bigger disaster. And the pictures you see here are, I copied it from a South Africa farm, and they were showing both the farming and effect on the penguin population there, which maybe personally we don't care, but these are the signals or symptoms which can affect us in a major way. I hope you are sort of mildly convinced that when we talk about climate and weather, we, not just human beings, but the total environment around us is affected one way or the other, and some of these impact and effect could be irreversible. So when we think about supercomputing, and that's why I had this thing in these brackets, it's not just one thing that you need, like a very powerful computing environment. it starts with a super problem, what you want to solve. Like in early days, 90s, okay, not for civilian reason, but for military reason, they had a big problem to solve, whether it was encryption and other thing. You need a major problem to solve and work. Then all the technologies aspects come in. So I call it super networking. Just imagine thousands and thousands of very fast systems working with each other. They have to be able to communicate very fast. I mean, you can think of, in some cases, multiplayer and other games. I mean, people, the desire of people to have faster and faster connection to their houses and other places, you can think. So these could be hundreds to 1,000 times faster in this case. You can't build these data centers. You need a special purpose facility to house these machines because of the cooling and the power requirements. And what you see in the middle are, I call super facilities. So I think in this case, this is a kind of a cloud system, and this is CSCS, and PISDINE, and someone opening. So you see only like a quarter or 1/20th of the machine room. And there are things above and below. At some point, today I didn't include in this talk, but if there's some other event, I can say how we get lake water to cool, because we have made a very sustainable data center. You have to imagine you have to store like tens of petabytes of data, because these simulations are, and you just can't store them like that. And then there are technology providers we work, and they are usually much higher. So in this talk today, I will focus on super problem and super processing. But that doesn't mean that other are less challenging and solve problem or less important. The reason I'm bringing all these topics here is, as you study, graduate, go on, you may end up working in different areas, but you may still be involved in one of the supercomputing areas. So I hope I got you hopefully enough excited and motivated why I'm talking about supercomputing, why it relates to us, why we have to fund, like in CSCS, both MedUSwiss and us, we are funded by taxpayer money. And the governments have to fund these activities. So before I go to the main part of the talk, oh dear. Yeah. I don't want to update anything. So, okay, we are good. Are there any questions in the audience? Okay, we can come back. So, like I said, I will talk about one grand challenge and then go into deeper on the computing part and computing requirements. It's more or less what I said before, but now I will distinguish a little bit climate and weather climate modeling and weather forecasting. These problems have enormous social and economic impact. So I have some pictures here, and what you see here is the flood in the US. The loss of human lives was not that much, but the business and disturbance and displacement. And so I have family in Houston. I lived in Houston. They still have areas where schools could not reopen yet in Irene. Some of you may remember the volcanic eruption a few years ago, where many hundreds and thousands of flights were canceled. This is like showing our drought in some area. And all in all, the problem is, not the problem is, the reality is the world population is growing quite rapidly. And it's the impact of these activities would affect a large number of human population. So it could lead into inter and intranational conflicts. I mean, it's been a prediction for decades that they say the next world war will probably start in Middle East around water sources and these areas. So now I'm going to distinguish, and I think you already probably appreciate a lot, what is weather forecasting and climate modeling. So I copy here is a way behaving with respect to human activities. So it can go for the next few hours up to 10 days. And they say every 10 years, the accuracy of prediction improved by 1 extra day. So we started with few hours in a few decades ago. Now every day, the accuracy of prediction improves. And this is what you see. So here I have this AccuWeather thing for Porto, which is more or less, I mean, I wasn't expecting what I expected this morning, but it's kind of okay. Then when you think of climate modeling, you want to predict patterns, long-term weather patterns of a particular area. And if you have seen this IPCC and other reports, so this is showing monthly mean outgoing long wage radiation. So in this case, what you have to think, in this scenario, you model for few days, maybe some cases few weeks. And you have the accuracy of regional part quickly. But in this case, you have to model hundreds of years going back and hundreds of years going forward. And this has a completely different requirement than this one, because these, as I will show you later, some of these scenarios are used for decision-making very quickly, while this one are more long-term decision-making areas. The other thing that we have to keep in mind is that this is the pattern that the population density is increasing. So even a small impact in urban area could have a huge influence. So I can again tell from my personal example. So in 2005 or 6, there was a big hurricane that happened in New Orleans, and they were not able to evacuate them quickly, and a lot of people died. After a month or so, there was another hurricane warning in Houston, and they were extra cautious, and then they say everyone evacuates. But there was no evacuation plan. They never realized how many people live there, whether they can get out of the city easily and quickly. And people spend hours and hours on freeways and just came back because they ran out of, I mean, Houston is a hot city, ran out of gas, they ran out of food, and then they came back, and the worst part of it, it never materialized, so there was no problem. So it's the reason I'm mentioning it is the accuracy is becoming very important here, because a lot of us are living in urban areas, and more will. And you have heard about planning for when concerts and other things like that happen. So this is not really related, but these types of topics can become very important, and you need to be able to predict very precisely what is going to happen. As I mentioned earlier, the number of passengers are increasing, and they reported that last year, that like nearly 4 billion people flew one way or the other. And we are some people travel a whole lot. I, for example, travel quite a bit. But you just have to imagine, it's like about half of the world population is on the move in one way or the other. So the impact of not being able to predict the conditions necessary for planes can have a huge impact. And this is what I copied from the Zurich airport. So they have their flight and figures on the airline. And here you can see number of passengers in million and number of flights in thousands. So you just see the number. And Zurich is, I would say, a medium-sized airport. And then they have the same number in millions going up and down through the year 20. And precisely for that reason, the Matthew Swiss, they moved their office, the Swiss Weather Forecasting Institute, I call it. They moved their headquarters, and now when I go for meeting to Matthew Swiss, I go to the airport, go through the passengers area out of the airport, and go and meet them outside their office, where all the air hostess and staff, they go there to, get there. In fact, the operations center of Mateo Swiss and the operation center for pilots and air control are next to each other in the same area. So I'll change gear a little bit and say, okay, as a human being, weather, climate, and these things are not new to us. Human beings have always been curious for their life and livelihood, what's going to happen, whether there's going to be enough rain or some extreme weather situation. And there are many nice, online or other books you can look up, but like in earlier parts, people will look at the sky for local conditions, or they will, this one shows a frog, so if a frog is behaving in a certain way, they will predict if it's going to be raining or not, or a nice weather. Then they started, these are the earlier sensing equipments, a barometer and other, and then they started introducing that at a very local way, what is going to happen. So it's called that storm glass here, and then they will read based on the pressure. And then in 90, or it still happens today, they started having these weather balloons going up the air for sensing different conditions of the weather. So you have these weather balloons, and I read somewhere that every hour there are 18,000 weather balloons launched all over these are things I think you have seen. These were the early computers. I think this is the UK Met Office they used. And then here you see the regional part, and here you see different possibilities. So they don't have to generate one prediction, but they have to generate multiple predictions, so they can see what are the extremes and other things here. And now what is happening here is, you can see the resolution has become much more cleaner and clearer. We will go back here again. And then they are also having different parts of ensembles and layout here. This is the UK Met Office machine, or ECM, I think it's ECM. Met Office, big supercomputer for weather forecasting. And now, it's not now, it's been a couple of decades, we have these weather satellites. So it's satellites going above and taking pictures, and these are also providing some of the information that comes in to do the weather forecasting. So what is the message here? And why am I showing you this? Initially, we had very few data points to make a decision or a prediction. Now, every second, we are getting so much sensory information from all over the planet that you need a lot of streaming, processing, storage, and computing power to predict what happens next. Just imagine a situation, and I remember while doing some research here, that the very first time the numerical weather prediction models were created, in order to do a forecast for next 6 hours, they needed like a day or two. So it's not good enough if you are forecasting an information that is pretty much useless. So you see this race and challenge in time. We want to be precise, so we have more sensory information coming to us. The models are getting more complex to compute and use that information, and then you have to make a precise prediction so airplanes can land and people can figure out what they do. And that's why this. So numerical weather prediction is the term that has been used for quite some time, and I used a little definition here from the website. So it says that you have to have a set of equations. So there is a mathematical model behind it, they have to write it into a computer code. They use equation. You have to use parameterization, because how would you say where the things start? Because all sensory information coming in has a different time scale in there, and boundary conditions, and then you run it over a domain. So this is from the Deutsche Wetter, is the German Weather Institute, and I like their figure because they showed the full range. So you have different observation centers in water, over satellite, and in between. Then you do something called nowcasting. You probably heard of it, and it's getting more popular as we are all connected via cell phones. And they say it can be accurate up to 2 hours. But this is the main part. So here what you see is the world is divided into grids, because that's how most numerics work. And then you make a model where you assimilate all the data here, and you do physics. Someone told me they are interested in physics, lots of physics here. And you make an ensemble system, meaning that when you do prediction, how many predictions you will make for different probability distribution. And then there are these intermediate steps where you do post-processing and communication, you do model processing. You have a workbench. So what is a workbench? It takes all the information and it says, because the information coming directly from a scientific code cannot be consumed by a layman person like me. How do I know this arrow and this bar and this color would mean? They have to translate into values which are meaningful for me if I'm, let's say, a pilot versus someone who is out in the sea versus someone who is just going about their business on an everyday way. And then you have, you issue advices, warnings, and I get them on with my MeteoSwiss app on my phone. And then there are various customers. So as I told you, MeteoSwiss, their biggest customers are the Swiss airport or the aviation one, general population, and hazardous condition and warning. And this is the whole tool chain work. And now you can think in this whole process, a lot of people are involved, from communication to equipments to anything in between that involves systems, software, mathematical models, and other things. So I will now go deeper into MeteoSwiss because, and trust me, I'm now going to talk about more supercomputing than, because I probably have given you way too much information, but I thought it would be important to know that how the technology and the needs are evolving. So MeteoSwiss started, I mean, it started in 1880 when they set up this center. But the first time they started setting up some very primitive observation center was 1864. And a year before that, they did their first publication in a newspaper for weather forecasting, a small table, but they did it. In 1994, they had a model with 14-kilometer horizontal grid. Because as I told you, to do these modeling, they have to divide the world. And now you see here, Switzerland is like just little teeny tiny here. So in the whole grid, you miss a lot of information, and that comes there. So in 2015, what they were doing, they were having what they call 7-kilometer model. So the grid was 7 by, and then they have some additional information about the precision. They were doing 372-hour forecast. And then in a smaller grid, which was more computationally intensive, they were doing one for 45 hours. And what you see here is kind of the mapping that goes from a model over Europe to a regional model to a precise model for MeteoSwiss. And MeteoSwiss uses a lot of additional information from ECMWF, which is the European medium range forecasting model. But even if you haven't been to Switzerland, you know that Switzerland has Alps. So it's not flat by any stretch of imagination. It's maybe also like here. So if you look at this 0 to 64-kilometer model, and you see, OK, 0 to 16 is here, if you divide the grid by Z, you will pretty much miss a lot of small valleys and terrains, and they will be considered flat space. And you can just imagine how inaccurate things could be, because you will miss the wind situation, you will miss the cloud, and all these other situations. So, and it is true for most places. So what MeteoSwiss decided, they say, OK, we need to go low resolution, because we are really missing our parts of our Alps, parts of our valleys, where that flood happened that I showed you earlier. And we need to see as local conditions as our methods and system and computation allow us. We need multiple ensembles, meaning that we want to know extremes, just in case. Because if we do few ensembles, few initial conditions. So overall, they predicted the system they built 4 years ago and going to their new system, they will need 40 times more performance with the same budget. So they were not increasing their budget to build and operate the system, but they wanted it to be 40 times as powerful. And that's what their calculation was. So they say if we go to 1 kilometer model, we need a factor of 13 more computing performance. In order to do more ensembles, where they wanted to do 21 ensembles here, they need a factor of 20. And they want to bring more data from the ECMWF, they wanted to need like a factor 7. And they did the factor 40 computation, because not all happens all at the same time, so that's why it's like that. And that's what they wanted to motivate their discussion. So if they do 1 kilometer model versus a 2 kilometer model, you can see the precision in the output, where here you will miss some regions entirely, and here, and in the 2 kilometer, the other side, you will miss a lot of local conditions, while here you have some fine edges in the weather conditions here. So what we said is, look, we can't solve this problem just by fixing one thing, because as some of you know, in computing, there is something called Moore's law, which is every 18 months, it's transistor density, and they say Moore's law has been dead for some time. But technology alone will not solve our problem. We have to do more than that, and there were multiple steps taken. And that's where I will try to highlight 3 of them. The first part is the code. Majority of these codes written for, especially for scientific simulations, have been written decades ago. As you know, as I told you, these problems are not recent problems. And this was the old version of code where there was a majority of code was in Fortran, and code has 2 parts, physics and dynamics. Dynamics was parallelized with a message passing library called MPI, and then they would run it on a system. So the code and the system was tightly integrated. And the problem was, if you need to change something in the code, you have to rewrite a whole lot of application. What they decided is we have to write a code in a way is much more modular. You may think, okay, we are computer scientists, we learned these things like 30 years ago, 25 years ago, you have to do object-oriented programming and all these things. But that's how scientific community is. They use Fortran to write faster code on a certain system. And then the code was partitioned, and some parts, and it was written in a way that you can run it on the CPU and GPU, and this part was optimized using OpenACC, which was the directive programming. So it was a real heavy lift. They started in 2010, and it took 5 years because it's several 100,000 lines of code. And not everyone knows, as I told you, there are mathematicians involved, physicists involved. Not everyone knows how, and validation can take a long, long time. So this was one of the things. The second thing was using a technology. Because we knew that we cannot just buy a processor with 10 or 15 gigahertz frequency. It would just even melt. And so these slides come from NVIDIA because they were very proud of this work, as well as we were. And the technology made a big impact here. So they say before GPUs were introduced, and I will tell you what GPUs did there, you would have a 24-hour forecast, 2.2 kilometer resolution, and 8 simulations per day with a low resolution where you miss like all these depths, and then you go again a 24-hour forecast with much higher resolution, and you keep the same number of simulations per day. The medium range forecast was 3 days ahead of time, 6.6 and 3. The medium range forecast went from 3 to 5 days, 2.2, which is down from 6.6, and they were doing a lot more ensembles to capture different conditions. So that was the second part. Here, the technology also became part of it. So all in all, there were several factors that improved this factor 40x. And the message here is this co-design and focusing and solving on a problem. And here he said there is no silver bullet, so there is not one thing that solves the problem. So they needed improvement in computing, they needed improvement in ensembles, and they needed improvement in data assimilations. These were the requirements. So 1.7x came from software refactoring. It was just rewriting the old software in the new way. And it was even faster on a CPU. So had we been running on CPU alone machine, this is the factor we get from doing that. 2.8 in mathematical improvements, resource utilization, meaning CPU and GPU. Change in architecture, 2.3. And the GPU-based systems now consumes less energy than the CPU-based system. Moore's law is this 4 years, and then we added more processors in the system. And the whole thing was done in the same budget. And the reason for me showing here in this specific talk is not that to say that, okay, we were so good, we did it, but that when you work on supercomputing and when you solve these problems, you could have different contributions. And in this specific case, of course, the driving force for us was the problem-solving nature, the main problem we wanted to solve, but there was the whole team coming together from Matthew Swiss because they were motivated and interested in doing that, and our vendor partners also that made many changes from NVIDIA and Cray in designing and operating, and also on the CSCS side in the operation and design part. And NVIDIA was very happy with that, so they made big, and still I think today, Matthew Swiss is the only 24/7 operational weather forecasting system that uses a non-CPU environment. And we are running since 2016 that thing. And because it was a co-design effort that involved really heavy lifting with application, the Swiss ICT Award, which is for all IT technologies, not just HPC and supercomputing, high performance or supercomputing, they realized this collective, and there are people from CSCS. I was at European supercomputing meeting, so I couldn't go there. They awarded this award saying that this is a piece of software and technology more like an appliance that resulted in the benefit of society for Switzerland, and they gave us this award. So now I'm going more into technology, and now you think I came from a problem to technology, and I will do a deep dive into technology now for supercomputing. But before I go there, are there any questions? And I'll take a little break. Yeah. Accuracy of? Whether the accuracy of the prediction has improved?
Yeah.
So this is a good question that I cannot answer precisely because you have to go back in time. So they have done some predictions back in time looking at this flood situation that I showed earlier, and they say, if they had done that many ensembles, they would have recognized some of those extreme conditions. But looking forward, can they prevent and predict something with more accurately? I cannot give you a precise answer, okay, this was the event that was predicted precisely or missed in other case. But what we ask our Matthew Swiss colleagues the same question, and they say that in most cases, Matthew Swiss products or the simulation results they provide, they have to be used as an input in future applications. And some of those future applications are rewritten for this additional information that is now being generated. And they say the bigger impact they just started to see now with some of their, in case, aviation partners, and some of the flood and critical weather warning situations. So I would not want to claim that everything has been improved by a factor 40 in terms of prediction and predictability, but there have been certain, especially looking back, they have definitely identified that had it been there long ago, it would have improved, but also going forward, their customers are requesting more of this information to provide as an input in their model, which is an evidence that it has improved the situation from an accuracy point of view. Anything else? Yes?
Can you hear me?
Yeah, I can hear you.
Okay, so you are saying that
Use the microphone because I think they are recording it. So. Yeah.
Yes, hello. So I was wondering, you were saying that, of course, in Switzerland there's a lot of altitude differences. So I'm from the Netherlands, so we don't have that issue. But then we have other issues, that there's a lot of water, right? So I was wondering if the algorithms are optimized to deal with altitude, for example, or if do they all use the same type of algorithms?
I will give you a high-level answer because I'm not a climate scientist. But my understanding from climate modeling and there are different reconfiguration they use. So in the US, when I was in Oak Ridge, their climate model was a combination of 4 models. One was a land model, one was a water and ice and other things. So I would imagine that these models, like the Swiss model, is essentially a German model. Cosmo stands for like a regional model that was mainly done in Germany. And Germany touches water, as you know. So I'm pretty sure there are elements of this thing. Now the main question here is whether the codes that have been, or algorithms that have been modified for GPUs extend all the way to parts which are required for modeling the conditions that will have a major impact in, let's say, Netherlands. I can't say. In theory, it's possible, but these codes or applications are rather huge that I have to check with someone whether the parts of the applications that were modified and refactored, in this case, extended to the entire model in there. And they are working now in moving to something different, which is called ICON. So, but that's a very good question. I will definitely ask who can take it when. Yes. Yeah.
Mm-hmm. I was just wondering, you were talking about grand challenges, and so the weather forecasting is something that definitely justifies the need for the supercomputing infrastructure, and it's clear evidence that the taxpayers' money is well spent. Are there any other big challenges that are being also used daily in these supercomputing infrastructures? I'm thinking of, there's the Human Brain Project that has been pushing a lot, or I don't know, maybe cancer, or is there anything that is actively being used and not just putting on a set of slides saying we will use supercomputers in the future?
Okay. So you have to wait until my second to the last slide for that part. But I will not be able, so, and then we have to take it offline, whether those domains or communities are just saying they can and they will, and whether they are ready or not. So I will come to those slides. Those details are not in this slide. So we are in CSCS is part of this Human Brain Project. And I think at this stage, when I'm kind of almost being recorded, I will say something politically correct. Yeah, there is ambition and need, but there are many steps needed to get there. Yeah, so just because you want to use, this is what I was trying to say, that weather and climate community, they have been using computing for decades, but just doing this little, I would call it little change from one way of operating to another involved a lot of people, a lot of man-year investment. And now just think of communities and technologies that have not been that sophisticated in advance and taking them, so that will be a big, much bigger effort in those communities. So, but I will come to that part, but those will be not detailed one. So this is the part I feel much more comfortable and relaxed because this is what I kind of do. And if you ask me, okay, Sadaf, what is your specialties? The performance modeling and networking communication, which is probably very boring part, but when you are excited about it. So here what you see is this list I mentioned, the beauty contest of supercomputing or World Cup or whatnot. So what they do is they use a simple, rather simplistic mathematical equation which does not involve a lot of computation and storage. And they have been, but the good thing is they have been tracking almost since 1993. They call it top 500 system, and it's based on this running this calculation called LinPack. But it's been happening much earlier. In fact, some people argued it even happening before, especially during the war times. But in 1950s and I would say prior to 1990s, supercomputing used to be a very, very exclusive club in the sense that you will go to vendors that will design all the way from piping and system to cages to software and environment that run on it. So these systems were really, truly vertically designed solutions. And it was really out of reach for many, many communities. For powerful, they did really lots of interesting things, and we wouldn't have been here without them. But what happened in around like 1995 or 6, they called this thing the attack of the killer micros. So what happens was that the processors that we were using in our desktops and the Xeon processors, they were commoditized. So HPC started becoming commoditized in late 1990s. So in 2000, we were still building rather boutique systems. We still do build, and this is the system that just became #1 from Oak Ridge. It has GPUs and CPUs. It's called Summit. If you have time, you can look up Summit ORNL in this system. But the performance, so this was the first petaflop machine, and this is around 200 petaflop machine. And these are the things. So it's been happening initially for they used some supercomputing for sensors and other, but majority was done for, how would I say, non-civilian reasons. And this is the old one, like I said, 2017 November. So they publish this list every 6 months, and this is the PISDINE. Why do I bring it here? Because up until now, what I talked to you about was an appliance doing one thing and one thing only, which is weather forecasting. And that is a 24/7 time-critical operation, so you cannot have multiple people messing around because otherwise the planes won't fly, another thing. PISDINE is a general-purpose supercomputing platform for researchers in Switzerland and beyond. And what happens is people have to write proposals, scientific proposals, to access these resources. So it's funded by Swiss research funding because in Switzerland and many other countries, they see computing and high performance and supercomputing as a tool to allow their domain researchers and scientists to be competitive in their respective field of research, as they would require a special equipment such as a light electron source or an observatory. So it's a scientific tool for many scientists and researchers to advance their science. And the idea is that you can be in a disadvantaged situation if you don't have access to best tools to advance your science. So what you see, there are some numbers here. I can go in detail, but that was less important. So it's a big system. So the first system we built in 2013 with 5,300 earlier generation GPU, very powerful network. Networking is, I think that's the main distinction that I would say that you need for building a supercomputer and file system. And this is what it is now. It has GPU nodes, it has multi-core nodes, again, faster network and system. And as I said, it's a very versatile system. It's a supercomputing system, but a lot is done there. It's used for visualization because of lots of GPUs. It's using post-processing. Because it has so many GPUs, people are doing a lot of machine learning, data learning applications. This is, user lab is a mechanism or a program through which scientists get free access to these resources. It's a competitive evaluation process. Praise, this is one of the tier 0 system for Praise, which is a European program that allows European scientists to apply and access resources. And there were some universities that used to have institutional clusters, one rack, few hundred nodes. And then they realized that building, operating a cluster inside an institute, first of all, you have to hire people, or either you use your PhD students and postdocs as sysadmins. And then they realized they are much more productive by buying into a big existing resource. It's not exactly like a cloud model, but somewhat. So we have many university and other research institute using Pistine in a rather diverse way. So we made it to be versatile. So although it looks like very special design system, the environment on top of it is like any other Linux environment. And who uses Pistine? And so I just picked up from our newsletters, because if you are really interested, CSCS, we publish an annual report every year. So you go our website and you can see who is using, because we are a public entity. So we even have to declare how much money we get and how it's being spent. So you see everything from scientific outcome to money matters. So this is an example where you see some University of Zurich researchers prepare data analysis Pistine on a seismic way. So they are using it. This is a group from Imperial College London. So they are interested in plane designs or efficient plane design, and they were using this for simulation. This is, and they are looking for different transitional state in again, a complex simulation, but essentially it's how do you do, how you define different materials for medicine and pharmacology. This is, I think it came in the brain research area, but this group is from Basel, and they are doing some of the cognitive neuroscience and other behavior research. And now more and more of these, what we call modeling and simulation methods, are using machine learning for initial condition and post-processing. We don't see it just now, but some of the tools are already required for that. But if you want to see a bigger, what were the other projects and publications, I would recommend you to go to CSCS website and look at the annual reports. Now I come to climate, because if you remember, I talked about weather and climate, then I just stayed with weather because that's what Matthew's machine's sole purpose is. But climate modeling is even, and it's about trends. It's how the earth is warming, cooling, and other things. And I told you there we were talking about days, maximum weeks, and very fixed. And because you have to make weather forecast when it's meaningful, or in the time frame it's meaningful. Here we are talking about trends, and for that you have to do centuries, not just decades. So the same code with different setting, because it was that question came earlier, climate versus weather. But the code is still the same, it still uses GPU. And there is this publication, and it's the first time it was done, and they set up what they call a performance baseline with nearly 5,000 GPU with the new version of Cosmo. And why this is important? And I think someone you all sort of partially asked in your question. It's like, how fast have you go and what would be the scientific, and how do you know what you need to, from a computational capability point of view, that target? So for example, in climate community, and we can apply the same in other communities, people know in some sense from their background or the models they have how much more computation power they need. But if you go into details, they cannot set a baseline, and they can't say, in 5 years, I need that much, and then I can do that much. It may sound very simple, but because of the complexity of the whole environment, they cannot say. So if you go and look at this paper, it sets the baseline in, let's say, 2017 now, and it says in 5 years and in 10 years, how far by a factor of, in some cases, 100, and in some cases by a factor of 500, we are off from the global challenges that are set at the international level. So this is like the computational baseline they set in this paper. And that was only where they were, and you don't want to set that baseline on a very, how would I say, on a platform that is not representative of the most powerful platforms that are out there. And this was very important. And now I think the most important thing that can happen is they can take this thing and set that baseline, or see the projection can follow for the new HPC system, which also uses BizDrive or GPUs. And this is the part that gets me really, really exciting. And I didn't want, maybe 10 years ago, I would have only started from here, but after giving talk in multidisciplinary environment, I thought it's not the best way to start here, because I can lose all of you just in minutes. So what's typically inside a HPC system? You may think, okay. So typically, again, it's a picture, but you will have a server. So earlier, say, turn off your laptop. Do you all know how many processors you have in your laptop? I think multi-core is, I mean, considering multi-core started in 2005-ish almost, we are, even on cell phone, I mean, the iPhone 10 is amazing in that regard. So we have lots of CPUs. In this case, so supercomputing systems are traditionally built with, we call it multi-processor, multi-core nodes. We connect them by a network, and then we connect multiple of them. A supercomputing blade is usually, I mean, you can build a supercomputer with 4U server, but it will be highly energy inefficient. But so typically, if you look at a Cray environment, you will have a very dense design. We call it a blade with network and everything. And then whenever we install, there are time-lapse videos, if you're interested, you can watch on YouTube, where they show how systems are being installed. So we rip out all the internal parts, run the cables. I don't do any of them. These are specialists. But it's fascinating to watch how quickly they assemble and build these systems, because you have to cable everything together, power everything up, make sure everyone can communicate to everyone and nothing sort of melts and blows up. So it's a fascinating thing to watch. Usually the cabling part is very interesting for me, because you have to think, you have to run like tens of thousands of cables. It's really fascinating that end of the day it works. Okay. Now I'm changing, and someone, I think during the break, told me, thinking outside the box. So we can build those systems, but they will, either we invest too much power and money, and we will have incremental changes. So if you look around, and I think for some of you, you were not probably born in the years that I'm showing here. Do you know which game is this one? Zelda? Okay. And this one? The Grand Theft Auto. Okay, good. So you see that the resolution and precision of the environment and the things you can do has been increasing. And behind this, majority of the part are these things called GPUs, or graphical processing unit. And in a way, there is some similarities with weather forecasting, because the more precise you want to do these computation and calculation, in a gaming, you cannot wait like 30 seconds for a frame to update. It has to come back very quickly. So it's kind of a weather and climate modeling type of situation. You're having more data to compute with, but you have less and less time to update. So it's kind of a paradoxical situation. If someone is interested, I can go into detail. But so they started designing these systems. And again, In this case, there was no grand challenge problem. The grand challenge problem was probably the desire of human being to play faster and more realistic games quickly in multiplayer and all these modes. But there was a lot of money and innovation happening in this area in the last, I would say, 2 decades. A lot. And you can see the result. I mean, I think anyone who is maybe even partially interested in movies or gaming and computing, you must be not interested in anything not to notice some of these advancements. So you see this thing happening over time here, powered by majority GPU. What happened was they introduced this term called GPGPU, because previously those graphics programming was done in a language, I would say, that was so different from scientific computing programming like C or Fortran. So GPU computing was introduced as general purpose GPU. So what some people in Stanford and other places, they started introducing what they call programmable layer. Because even if a device is powerful, and it will come back to when we discuss quantum computing and neuromorphic computing, just because you have a powerful system doesn't mean you can use it, or like an end user can use it immediately. And they introduced these languages, and in case of NVIDIA, they introduced a C-like interface, which is called CUDA. And suddenly, this performance was available for anyone having a GPU in their laptop, desktop, or other. And they cost like a few hundred euros at best. Of course, the ones we have on PizDiant are not that one. So this is what happened. CUDA was launched in 2006. And that was the start of general purpose GPU. There was research going before that, but that was kind of the start. And I think it was Japanese who built this system, and then they ran it. And this was the first chip. And then there are systems going around, so this was the Oak Ridge. But then you see a bunch of AI and machine learning and deep learning started coming in. And I mean, I put Bitcoins in there because a lot of systems doing Bitcoins are based on this thing. And now you see the whole area of which may not necessarily require supercomputing, so you can do it in one big server and system, but that process started happening in that thing. So GPUs that were doing graphics for, I would say, entertainment reasons precisely, were being used now for general purpose computing. So if you haven't done, let's say, GPU programming or not much of CPU programming or designed a system, how does it look like? And I will try to here be very high level and may oversimplify for some of your, the horror of some of you, but please bear with me. So typically what you have on CPU, I mean, here I'm trying to highlight the differences. You have 10 of computing elements on core, and here you have thousands of them. These are but powerful cores, so because in your when you are doing more interactive jobs in your, like editing a document or browsing another, you may not need it. You need but a lot of RAM or memory to keep feeding your multiple applications you are doing, and you have some memory bandwidth. In case of graphic processor unit, you have you can think of thousands of working bees here. They are simplistic cores, they are good at few things. You have less memory, and you have to use it in a different way, but you have a lot more memory bandwidth. So you can bring large chunks of memory, but the latency is high. And traditionally, it's an input I/O device, while CPU is the controller of everything. That's how we design the operating system, that's how system works. So essentially, CPU is the boss. It's like the manager or a controller that controls everything, including the GPU, what's happening on the GPU. While GPU is an output device which is doing a lot of computation for very specific things extremely fast. That leads to some issues because now the things we are interested in doing is happening here rather than here. I'm just checking so I don't run out of time. So if you design an architecture or a system, what you have, I mean, you can map it into anything, whether it's your cell phone or your laptop or anything. You will have a CPU, its local memory, which is really nicely abstracted, and then you have a GPU with its own memory, and it's driving the structure. So I chose an example called matrix multiply here. It's a simplistic enough scientific or mathematical calculation, but it's used a lot in many modeling simulation as well as in machine learning and deep learning applications. It's like a basic building block here. So when you do this computation on CPU, you just assume these matrices are going to be in your RAM. You don't have to even worry about how you initiate. I mean, of course, if you care about performance, there are many optimization tricks, but just for the sake of simplicity, you just define your matrices. I mean, it's not a real code, so you have to do some more work. And then it should be 0. Then you just iterate over until your output matrix is calculated. Plain and simple. This is not an efficient course. You have to do a lot, but the idea is there. But if you do it on a GPU, what you have to do, when you start, you have to make sure that you send data in an optimal manner from a CPU to the GPU where work is being done, and then you get it back. And then when you write a GPU code, you first write a CPU code. And then you have to lay out so that you can move big chunk of memory, because that's what I said, this is the main difference between CPU, because latency is high. Again, I'm not trying to teach you matrix multiply on CPU, GPU. I'm just trying to highlight the differences here. And now suddenly you have to write more code. You have to know how things are moving around, not only within a GPU, but before and after, and that becomes complicated. And just imagine hundreds of lines or tens or hundreds or thousands of lines of scientific applications have to be done this way. And it gets even more complicated, because when we do supercomputing or parallel computing, we are not in one server or one laptop or one system. We are communicating with thousands of them. So when you are on a CPU system, and usually for communication we use MPI, you just send data, an MPI message from a CPU to another CPU. Nice, simple command. But when you do it from a GPU, a whole lot of things have to happen. Because from a GPU memory, it has to go to a CPU or some intermediate memory. Then it goes over the interconnect, and then it goes back to the other one. There are solutions emerging, but still, there is a fundamental operating and system design where we can't prevent it. So essentially, when we build a supercomputing system, we take a bunch of these thousands and thousands of these servers and connect them through a high interconnect. This is the MPI, is the message passing communication, and this is what happens if you do it in a very inefficient way. And we as like people who are programming, they have to hide these days. And PCI is the communication bus. So when you have multiple GPUs, they can communicate. Now they have introduced new technology to communicate things faster. So you have programming challenges, you have communication challenges, you have I/O challenges. And then you have debugging and troubleshooting challenges. So the devices exist, like NVIDIA have their debugger, their profiler. And if you are writing your code on one system, it works. But if you work it on a code with multiple MPI, like for Swiss code, where they have CUDA, OpenNCC, MPI, GPU Direct, there is no code that exists that can debug this solution. So you just have to, taking that heroic effort in Cosmo is filled with many, many challenges. And innovation in each and every field can make a huge difference. So I stop here, and I have 2 more slides only. But any questions, comments? So I'll continue, then we can stop. So what's happening in future? Again, going back to my initial, how you said, thesis. Innovation in computing are being driven by grand challenges, or supercomputing, I should say. And there are many. And as that question was asked earlier, I don't have any details. Personalized medicine, for example, it requires mixing and matching many, many patients' profile with their reaction to medicine, where they live, or their environmental condition. It requires a lot. And the most difficult part here is the security. So we are going to be dealing with highly personalized data in a shared manner. And it's posing a lot of challenges. Someone told me the other day, I was in a security conference, they say, if someone steals your credit card, now the system is efficient, you can change your credit card. But if someone steals your genomic or some kind of other personal information which you can't change, what do you do? So it's becoming a very interesting area for hacking and other. Investigating these diseases. You have to do complex multi-level simulation. And this is the earlier question. Can they use supercomputing? These communities are far, far. I mean, they have to invest a lot in their, how would I say, pipeline of mathematicians, code developers, and parallelization methods to get where some of these communities are. Climate and weather, we talked about it. Renewable and sustainable energy. So as most of us know, I think there are many technologies that exist, and every now and then now we hear news that there is an oversupply of solar-based energy, or there is an oversupply, and we cannot put it in the grid because grids are being, it's going to stop? Okay, I see something here, it says, in 52 seconds, it will stop. Okay, let's just go. AI, machine learning, we talked about it. I mean, it will have a societal impact. Okay, we can take it as a threat, meaning that it will take away human jobs. But as the societies are getting older and we rely on different technologies, I think, I use self-driving cars as an example, but for our household and other things, I think these technologies will improve our life with some side effects, but I strongly believe, and the global warming impacts. And you are very fortunate here that you will go and learn today. In 16 seconds, it will stop, so I will just be quick. We have to, apparently, we need spatialization. So we cannot build one CPU and solve everything. So this is inside an iPhone. It has 6 cores, and it's optimized for something. Okay, so it closed, I'm still okay. And this is what we are thinking about. As we are solving a range of these problems, there will not be just one processor and one GPU, or one design that will solve it, or one programming language, or one method. There will be a combination. You know about, there will be talks today or in the week on quantum. It's fascinating. It's exciting. It's so abstract, people don't understand it, but to me, that's the most fascinating part of it. But it's going to solve a kind of problems that are very inefficient to solve. And we will heard about neuromorphic computing in that way. And they have similar rich issues for dealing or tackling this whole stack from mathematics to writing codes and operating systems that we will have to deal with. With that, I will stop and then take questions. Yeah.
There's obviously some time for questions.
Yeah.
We still
Yes.
have 15 minutes for questions. So
I have a question. To what extent is the use of supercomputing to mine Bitcoin sucking up a lot of the power that could be used for other purposes?
I'm almost 99% confident that it's not happening at CSCS. Because we track which applications people run on this thing. But the question is really kind of a valid one. So commercial providers are going after, money-making ventures, and Bitcoin is kind of one of them. And what I remember reading, I mean, it's not always a negative thing, but I remember, or it was a program I watched, that there is a French company, an NGO, that are trying to raise funding or money for some of these humanitarian projects by buying computing time in Iceland, because where the temperature conditions are optimal for running high-performance computing and generating Bitcoin so they can be used for humanitarian reason. So to answer your question, I'm a technologist, so I'm not personally against it, because Bitcoin for me is a technology, and I think that is the future of monetary thing. Our monetary future I would like to see. And just like gaming, if some innovation can come in that can have a positive impact on what we do for basic sciences, such as based on modeling and simulation, and what we are doing in AI and machine learning, I would support it. So I didn't answer your question in the precise term, how much which is going now can impact it, because I think the innovation that is happening for Bitcoin, let's say mining, in application-specific integrated circuits, communication, and other, will benefit the science in general.
Thank you.
Yeah.
Good morning. It's okay. So first of all, congratulations for the nice talk. My question is very related with sustainability. So from one end, we have these super problems to solve. For example, energy, the climate change, whatever. But on the other hand, we also have these resources who are super powerful, but they also interfere with these sustainability problems. For example, computers, we have lots of problems with chips, with batteries, with energy consuming. How would you be your, I don't know, solution to solve this? Because I hear that in your center you don't use that power at all, from what I see in the slide 22 or something. So how did you manage to have a super facility, but at the same time a sustainable one?
I think that's a very good question, because it is bringing the point, and I didn't go to the facility part. I kind of mentioned Iceland for the facility part. So at CSCS, I mean, I will be a little bit joking here. Yeah, we don't run it on goodwill. So it uses power, and we get power from a grid, and it uses cooling, which we have to pump from the lake. But the design was, I would say, holistic. We knew we are going to design a data center that could, if we are not careful, can end up consuming more or environmentally more unfriendly than if we don't think about it. So for example, at CSCS, right now, I think we are almost all hydroelectric for the most part. Even our building, we are recycling cooling. So yeah, and then for that, you have to work with your energy grid in that environment. So because we are not an energy generator per se. So, but this was kind of the part, and then in that scenario, at the government or national level, then you have to partner with energy provider and supplier. On the cooling side, because if you look at if you are interested in the efficiency of computing, if you are using more energy to cool down your supercomputer than you are, and using for running it, it's a bad thing. It's like an overhead energy. And in the system, in the data center design, the data center is fairly new. It was built in 2012, so you could learn from other people's experience. But what we said, okay, what could have been the most sustainable form of I would not say economic, but more sustainable form of cooling where we do not have to use a lot of air conditioning and electricity to generate cooling. And then at that point, it was decided that we use very, very deep down, I don't know how many kilometers down, where the water temperature in the lake is about 7 degrees or even less. And then we pump it to the data center for cooling. And again, there are many processes involved. It's not a rather straightforward process. And so upfront, it was more expensive to set up that environment. But in the long run, it will pay off, as a typical data center lifetime is 30 to 40 years. So those type of decisions one can make by doing that. If you're really interested, I would really recommend you to watch some videos or programs that are available online, how some of these hyper data center from cloud companies like Google and Amazon, what type of technologies they are using. The thing we can't use their type of methods is their systems are rather sparsely designed. Ours are more dense design. But there is a lot of, in fact, AI is used to optimize those processes. So you have to work from a design point of view in both aspects. How do you get cooling and how do you get power with then other providers and suppliers? And we were fortunate enough that it was a holistic design that was thought even before we started building the data center.
Thank you. Leon from Delft University. First, thank you for your great presentation. I have a question about these system architectures you were talking about. You showed some slides about the networking and the interconnects. How do you actually optimize your system architectures on, well, both like rack level or maybe even blade level to like the complete system level to get optimal performance for, of course, the least amount of energy?
Okay, that's a very good question. So the network design we have in PISDYNE is completely different from what we have in the Meteosys system just because of the scale and sizing. So when you design a system where you think you will have racks and racks of nodes, or thousands or 10,000, or you call them communication endpoints, what you don't want is that you have a lot of bandwidth communicating someone who is near you versus a lot more latency going if you go. So you try to minimize the hops. So if I go from here to the other 10,000 communication endpoint, so you do different level of optimization. What is the local level is called NIC, the network interface card, the thing that talks to your processor server. Then the second level comes from routing switches or routers. So when network packets come in, I mean, we all know the concept of router in our home environment, but these are optimized for this MPI. So in PISDYNE, we have a topology called Dragonfly topology. It's a topology which allows you to minimize hops and then maximize, that means minimize latency, but you can also pass through network traffic quickly. So if you're interested in these network design, you can look at, of course, the technologies of networking, which is InfiniBand. Ethernet is also changing, and some of the proprietary one like Cray. And then you look at topologies, the design of the routing and switches, and then the design of some of these communication protocols. And this is one of the most active, I would say, area of research in parallel high performance computing in the area. So processors, they don't care what type of network you are putting in there, except, okay, you have to have an I/O bus fast enough to connect it, but rest of the work is taken care by these routers and switches. And in PISDYNE, we knew we will build a bigger system, so if we didn't opt for local optimization, we opted for global optimization, because if you choose a topology which works in let's say hundreds of nodes, but to go to thousands of nodes, it will cost you 10 times. You don't want to do that. So there is a cost element that you consider from cabling and switches in that part. So if you look at PISDINE, that's how it works. In fact, in PISDINE, it's rather unique. You have the network and switch in the same chip. Typically, these are two different pieces of hardware.
So, so we're talking about sustainability in terms of the environment. There's, I think, another interesting side of sustainability. How do you ensure that you have political sustainability? So, how do you make sure that you keep being funded? Because for most of us, when we think about weather, we just type on Google weather portal and we get the weather. So we don't really realize that there's that massive infrastructure producing all these predictions. So how can you make sure that you keep being funded and that people know that what you're doing is actually important for their daily lives as opposed to funding soccer stadiums?
Yeah. So I will give you my personal view because I'm usually not that much involved on that's what I say, my job is to make things work, not to ask for money. But I'll give you my perspective because having worked and lived mostly European and then in the US. Yeah, when you have non-civilian mission, and depending on the country, like in the US, it's easy-ish, also in China up to some extent. But then you can have a local situation. So in Switzerland, why do taxpayer fund PISDINE, for example? And as I said, it's considered part of something that is very important to the society, which is science, research, and innovation. And it's considered an important part of that, I would call it an infrastructure, because scientists, whether they are researchers, PhD student, postdoc, or federal research institutions, they will be at a disadvantage if that resource is not there. For Matthew Swiss, yes, you can imagine for us, we can always go and look up Google because whether it's weather.com, AccuWeather, they are selling their services to, they are buying, selling at a commercial level. Why do you need a national one? So in Switzerland, it's a federal service, but as I understand, in France and many other places, it's again a federal service because it's part of the national security. For various military type of thing, weather is equally important, whether it's in your country or the country you are not necessarily fighting with or engage with them somehow, it's important to know the weather ahead of time. So to me, going back to the question of how would you sustain funding to build the infrastructure, it can become either part of a dialogue where either you are providing these competitive advantage to your student, researcher, small, medium enterprises. We do work with some of them. We cannot make money at CSCS because we are a research-funded institute. But some of the early small, medium enterprises can come so that they can use advanced technology. Or then you can have a local, national mission type of activities. It could be climate weather, and it could be some other local activities where you will make a relationship. I think the important thing here, and this is a big dialogue going in Europe, is how national resources are becoming available at a European-wide level. And if I remember correctly, Jean-Claude Juncker considered HPC or high performance or parallel computing as one of the pillars of future science and innovation. So somehow we need to also politically find a way, as I said, I'm not that much involved, that if it is such an important pillar at the European level, how we can take some advantage or benefit at the local level, being in, let's say, Portugal or Porto. Because I can find the precise phrase, but it's one of the, I think he had 2 or 3 bullet points, and HPC was one of them. And there are several initiatives there. So, but sustainability is kind of a, and at CSCS level, that's why we have publications and to always not prove, to always demonstrate what type of scientific outcomes are coming out of BizDyne, which are usually in form of high impact journal publications, for instance, and the collaboration. One thing I would say, just as a closing thing, as a personal note, this area of supercomputing or parallel computing is very international. So if you end up working in this area, you will have so many collaborators all over. It's a smallish community, but this is a very active, strong area of research and other collaboration. So that is kind of important. So you just don't look at inwards locally, but you can also have a bigger perspective. Because Switzerland is not such a big country, again, with a lot of investment here, but you can have a much bigger impact at different levels, not just by having a fast system, but at many other levels.
Thank you. Let's thank our speaker again for a great talk. So,